Okay, last week we studied two cycles. One is Otto cycle and the other one is diesel cycle. And we learned, how they operate. And we are going to thermodynamically study them using a simple analysis that is called air standard analysis. So this air standard analysis is a very simple analysis with a lot of assumptions because the actual internal combustion engines are very complicated, so we have to rely on computer simulations. So to study them, analytically, we are going to use these simplifications. So let's see how we did. So we are going to assume that, the air is the working gas and it behaves like an ideal gas. So that means that we can use ideal gas equation. And we are going to replace this combustion process, which makes it complicated, by a heat transfer from a thermal energy reservoir from, and we are going to neglect intake and exhaust processes. So it's going to be a combination of compression process and power, the process, which is a expansion process. And the cycle is going to be completed by constant volume heat transfer. And all processes are internally reversible. That means that we have two different processes. One is constant volume heat addition or rejection, and the other is isentropic compression or expansion. Okay. With one very special analysis is called cold air standard analysis. In this case, we are even more simplified, this air standard analysis, assuming that the air specific heats are constant. So there are two different ways to solve internal combustion engines by analytically. One is just air standard analysis. The other is cold air standard analysis. So this one is way more simple because we are going to use constant specific heats, but we are not going to use cold air standard analysis for Otto cycle or diesel cycle. Maybe we can use it for gas turbine later. So until then, we are going to focus on, we are not going to consider cold air standard analysis. So this one is only for gas turbine. So let's study Otto cycle and diesel cycle, starting with, to begin with, air standard Otto cycle. Excuse me. It has four processes: isentropic compression, constant volume heat addition, and isentropic expansion, and constant volume heat rejection. So always when you do air standard analysis, please use two diagrams. They are PV and TS diagram. And PV diagram looks like this. We are starting from here, number one. Let's start from here, number one. That's a state number one. And I'm going to say we have a piston. Looks like this. So this is where piston is at the bottom dead center. This one is bottom dead center. When the piston is at the lowest position. So what's going to happen is that the piston is moving between these two, bottom dead center and top dead center. That's how we produce work. Okay. So the first process is isentropic compression. So we are going to compress the system. So what's going to happen? when you compress this working gas, which is air, by pushing this piston to the left-hand side, the pressure goes up. The pressure is this vertical axis. This pressure goes up and this volume goes down, right? So process 1 to 2 looks like this. So there is state number 2. So this is isentropic compression. So moving this piston from here to the top dead center. Top dead center. On this TS diagram, it is an isentropic compression. So isentropic means entropy S remains constant. Entropy is the horizontal axis. Entropy S1 remains constant. So this is S2. So process 1 to 2 goes up because it's a compression process. Temperature should increase. So there is number 2. Then let's look at the second process. The second process is process 2 to 3, constant volume heat addition. So it's a constant volume. This volume V remains constant. V2 is the same as V3. So what happens when the piston is at the top dead center? The volume of the system is going to be this small. It is on the extremely high pressure. So then this spark plug ignite this fuel and air mixture. So there is a combustion takes place. In this air standard analysis, we are going to replace this combustion with constant volume heat addition. So the volume remains constant and heat is added, therefore pressure goes up this way. So there is number 3. On this TS diagram, heat is added between 2 and 3. So temperature should go up. What happened to the entropy? What measures entropy? Entropy shows how much waste energy in the system. So heat is added. Heat is a waste form of energy. So when heat goes to the system, that means waste goes to the system. So it gains more waste. That means that entropy goes up because more waste energy, that means more entropy. Less waste energy, less entropy. So entropy should increase because heat is added this way. And temperature goes up, of course, heat is added. Number 3, then process 3 to 4, isentropic expansion. This is when we produce work. So this is an expansion process. Therefore, volume goes up, pressure goes down. So this way, the piston is moving to the right, so it produces power. So this one is going to be connected to this crank shaft, rotating it, right? So that's how we produce power. To number 4. And on this TS diagram, this is isentropic. Entropy S remains constant. S3 should be the same as S4. And it's an expansion process, therefore temperature should go down this way. And we have number 4 here. And finally, the cycle is going to be completed by constant volume heat rejection from the system. So heat is removed at constant volume. So volume V remains constant. V4 is the same as V1. Heat is removed, therefore pressure goes down. On this, heat is removed, therefore temperature goes down. And entropy goes down because heat is a waste form of energy. So you are removing waste from the system. Therefore, entropy goes down. Again, waste goes up, entropy goes up. Waste goes down, entropy goes down, right? So this way. So it completes Otto cycle this way, okay? So initially, process 1 to 2, we are providing work. So work goes in to compress the system. And there's a combustion. Pressure goes up. Now it's going to expand. Let's produce work. And then waste heat is going to be removed. Now, provide work. Compress it. Combustion, which is a heat added. Pressure goes up. Now, the expansion, produce work, and then waste heat is removed. That's how this Otto cycle works. Then let's talk about the energy balance equation. How can you study energy balance equation? There are two energy balance equations that we studied in thermodynamics. One is a closed system. The other one is an open system. So is it a closed system or an open system? How do we know whether it is closed or an open? We asked this question many, many times. Closed system means mass does not change. So what happened to the mass of the air in the piston cylinder device? Is there any change when piston is moving back and forth? No. So it's a closed system. When you have a closed system, the energy balance equation is going to be Q in plus W in minus Q out minus W out is mass times U2 minus U1 plus moving boundary work. Do you remember this equation from chapter 3? Yes, we do. But not just this one. We have some, special cases. What about if you have constant volume process? It's going to be mass times U2 minus U1 because there is no moving boundary work. What about if it is constant pressure process? It's going to be mass times H2 minus H1. So this is the energy balance equation for a closed system. So now let's study this energy balance equation for each process. You can apply energy balance equation for process, right? Between two states. So we can apply this one for process 1 to 2, process 2 to 3, 3 to 4, and 4 to 1. So 4 energy balance equations. So let's go with process 1 to 2. What is that? Isentropic compression. So there should be compression work. That is moving boundary work, right? So process 1 to 2. We have a moving boundary work. What about heat transfer? No, there's no heat transfer here. There's only one heat transfer between 2 and 3 and heat rejection between 4 to 1. So there's no heat transfer between 1 and 2. So there's no Q in, there's no W in, there's no Q out, there's no W out. So it's going to be this one. 0 is mass times U2 minus U1 plus moving boundary work. There could be other moving boundary work in the cycle. So let's say this WB is going to be between 1 and 2, W1, 2. So this is the energy balance equation. Let me rewrite it. W12 is mass times U1 minus U2. Okay? Oh, there's one mistake that I made. It's a compression process. Therefore, it should have a negative sign, right? U2 minus U1, there should be a negative sign in front because it's a compression process. The moving boundary work is negative. When it is a compression process, moving boundary work is positive when it is an expansion process. And the next one, process 223, what happens? Heat is going to be added between 2 and 3. So we have a Q in. Is there WB? No, it's a constant volume process. So mass times U2 minus U1. Q in is mass times U2 minus U1. However, it is between 2 and 3. So Q in is mass times U3 minus U2. Q is mass times U3 minus U2. Let's say this Q in is between 2 and 3. So Q23 is mass times U3 minus U2. What about 3 to 4? That's an isentropic expansion. So we have an expansion process. So we have a moving boundary work. We have a U4 minus U3, but there's no external work or heat. So we can say M between 3 and 4. So M U4 minus U3 plus moving boundary work. In this case, moving boundary work. In this case, between 3 and 4. So let's rewrite this equation in terms of W34. W34 is going to be mass times U3 minus U4. Finally, process 421. Process 421. How do you determine that? 421 is a constant volume heat rejection. So we have Q out and constant volume, this one. So this is minus Q out is mass times, it is between 4 to 1, not from 1 to 2. So it's going to be U1 minus U4. This Q out is going to be between 4 and 1. So we can replace this by 4,1. So let's rewrite this equation in terms of Q41. Q41 is N U4 minus U1. So these are the 4 energy balance equations. Then, how can you determine its thermal efficiency? How can you evaluate the system? Thermal efficiency can be determined by desired output over required input. You remember that from chapter 5? Yes, we do. And what is desired output? W net. What is required input? The heat transfer into the system, Q23. So what is W net? We produce work between 3 to 4. We consume work between 1 and 2. So W net is going to be W3, 4 minus W1, 2. So this desired output is going to be W3, 4. This one. And U3 minus U4 minus W1, 2. And U2 minus U1 divided by required input. Q23, this one, and U3 minus U2. So, that doesn't, too small, right? So let me write it here. n U3 minus U4 minus n U2 minus U1 over n U3 minus U2, and you can cancel m out. So that's how you determine the thermal efficiency. This is how you do, this is how you analyze Otto cycle thermodynamically using air standard model. Any question? Then, when you study this Otto cycle, why do you want to study Otto cycle thermodynamically? To see if you can improve their performance. How can you improve the performance? As you can expect, the enclosed area represents the network that you develop. So if you enlarge, if you increase the enclosed area, you will improve the efficiency. So let's see how we can improve that. If you look at this piston cylinder device, is there any simple way to increase the area? There's one thing. What about if you move this top dead center to the left? You can do that. So this is the original top dead center. I'm going to move this one to even further up to this one. Then what's going to happen? The compression, you can compress this here even much more, right? So you compress more than this PV diagram. So we are moving to this, moving to this, moving to this compression ratio. This PV diagram, we can add this much work. So increasing compression ratio is one very significant way to improve the efficiency, to enhance the efficiency. Then the ratio between the volume when the piston is at the bottom dead center and the volume when the piston is at the top dead center, that is called compression ratio. So let's say this volume is V2. Let's say this volume is V1 here. V1 over V2 is the compression ratio R. So if you increase the compression ratio, you can move this one to the left-hand side so you can increase the enclosed area. So whenever you have a internal combustion engine, increasing the compression ratio is the easiest way to improve this efficiency. So if you have a car, you are designing its engine, you know that if you increase the compression ratio, you can increase, you can enhance the mile per gallon, the efficiency. Then, can we do that all the time? Not necessarily. The problem is here, spark plug. What this one does, it ignites the air-fuel mixture, right? So if you compress too much, then before this one ignites the air-fuel mixture, due to high pressure and high temperature, it's going to self-ignite. So is that good? No, it isn't. That's called knocking in the engine. Then we are going to discuss it later. So because of that, we cannot just indefinitely increase the compression ratio. There's a limit for this type of engine. Then, is there any way we can improve this compression ratio further without causing that problem? The problem is that you have a fuel here that will experience high temperature, high pressure. What about if you don't have a fuel, just air? Can you compress further? Yeah. Is there combustion? No, air cannot, undergo combustion alone. So let's just add air and compress as much as we can. So we can achieve extremely high compression ratio. Then when it is extremely high pressure, let's inject fuel. That is diesel engine. So in diesel engine, we have only air during the compression process. When it reaches the top dead center, then we inject fuel. Then due to high pressure, high temperature, the fuel is going to self-ignite. That's how we produce power. Okay? So before we talk about the diesel engine, let's solve one problem together regarding this Otto cycle. That is this one. By the way, there's not much thing I can do in terms of problems in this chapter. So, what we are going to do is going to be pretty much, what you will do in the final exam. Okay. By the way, is it too fast? So it's going to be, the best if you can just write this one down on your formula sheet and then use that formula sheet solving any problem. So you get used to use that formula sheet rather than making a new one on the day of the exam, because then you need to find, the weird one you need to look for, right? See? So make a formula sheet first before solving a problem. Okay, so whenever you hear air standard Otto cycle, there's two things that you need to do. The first one is PV diagram. The other one is TS diagram. So let's do that. PV first. PV diagram, and the other one is TS diagram. PV diagram looks like this. TS diagram looks like this. So 1, 2, 3, and 4. That's 3. 1, 2, 3, and 4. One characteristic here is going to be this volume V2 is the same as V3. Here, constant volume process, V1 is the same as V4. And constant isentropic process, S1 is the same as S2. Isentropic process, S3 is the same as S4. And you remember there are 4 energy balance equations. So these are the main equations that we are going to use in this problem. So basically, what you need to calculate is M, U1, U2, U3, U4. So M, U1, U2, U3, and U4. These are the 4 parameters that you need to determine first before even look at them. Okay? So let's do that. The mass of the system. If you read the problem statement, we have a P1, T1, V1. If you know P1, T1, V1, can you determine M? Yes, it's an ideal gas. Ideal gas equation. PV is MRT. T1, V1 is MRT1. What is P? 1 bar, 100 kilopascal. What is V1? 400 centimeter cube. Oh, you don't like centimeter cube, right? 400 divided by 100, 100, 100, 3 times, right? Meter cube. And gas constant R, 0.287 kilojoule per kilogram Kelvin. Remember that. Or you can calculate this gas constant from universal gas constant R bar over molecular weight. By the way, R bar is always 8.314. Molecular weight can be found from table A1. Just for your information. Temperature T is 290 Kelvin. Now we have everything. Can you determine the mass? Yes, we can. Where are you? Okay. So let's find mass. 4.806 times 10 to minus 4 kilogram. Any question finding this mass? Not much, right? Very straightforward using the energy ideal gas equation. Now let's find U1, U2, U3, U4. If you use air standard cycle, the main table that we are going to use is table A22. I will provide this table in the exam, so don't worry about that. Table A22. So let's go find table A22. Oh, here. Table A22. Let's see. Oh, what do we know? At the initial state, we know temperature T is 290. Okay, temperature T1 is 290. If you know the temperature, then you can find its specific internal energy. So temperature is 290. What is U1? 206.91. Let me show you this one. When temperature is 290, U1 is going to be 206.91. So let me write this one here. U1 is 206.91 kilojoule per kilogram. Then what else? Do we know the temperature at number 2? We don't. But we know the maximum temperature in the cycle. Where is the maximum temperature? The temperature is on this TS diagram. What is the highest temperature? Number 3. So we know T3. T3 is 2,200. So down here, T3 is 2,200 Kelvin. Can you find U3? Yes, from the same table. So where is 2,200? This is the temperature, 2,200. Oops, we don't have it. Then we go to the next page. 2,200. No, 2,200. Oh, right here. So we found 2,200. What is U? 1,872.4. This one. 1,872.4. 1,872.4 kilojoule per kilogram. So we already found U1 and U3. So if I grade your the exam, it's going to be this way. So if it is a 10 points problem, 1 point, 1 point, 1 point, 1 point, 1 point, or 2 point, 2 point, 2 point, 2 point. So you need to make sure you show how you got these properties. Don't just show the numbers. Oh, this is the temperature. So I got this table. I got this number. And U2, do we know the temperature at number 2? Unfortunately, we do not have. Then, what do we know? We don't know anything. So that's a problem. Let's see. The compression ratio is 8. What is the compression ratio? The volume ratio between bottom dead center and top dead center. And we have some information and V1. So let's find the relation between V1 and V2. The compression ratio R is going to be V1 over V2. And this is what? 8. The compression ratio is 8. And what is the relation between 1 and 2? Isentropic process. If you go back to chapter 6, when you have an isentropic process, chapter 6, when you have an isentropic process, let's say S1 is the same as S2, then there is one equation, two equations actually. When you have an isentropic process, there is one relation. V1 over V2 is VR1 over VR2, or P1 over P2 is PR1 over PR2. If you don't remember that, now you have this one here. Or go back to chapter 6 slide, you will find these two equations. Then, since we know the volume V1, so let's see if we can use this relation. I'm going to write this one here. Oh, it's written here. V1 R1 over VR2, that is 8. Do we know VR1? Oh, we do not know. However, we know the temperature at number 1. So let's go to table A22 and see if we can determine VR1. So this is table A22. At 290, VR is 676.1. So this is VR1 at this temperature. So whenever you know the temperature, you get all the values. So it is important to know the temperature at each state. So VR1 is what? 676.1. And this is 8. So can you determine VR2? Yeah, we can determine VR2. What is VR2? VR2 is going to be 676.1 divided by 8. That is 84.5125. Now, can you find U2? Now, yes, because you know VR2. You go to table A22, find this VR2. Whatever the U next to it is going to be U2. So let's find 84 for VR on this table. Where is VR? Here. 84. It's not here. 84. Right here, between these two numbers. Right? 84.5125 is between these two numbers. And what do you want to determine? U. So that U should be between these two numbers. So how are we going to get the exact U2? Linear interpolation. So you will do a linear interpolation in the final exam. All of you know how to do linear interpolation, right? So let's determine that. If you do, you get 475.11. 475.11 kilojoule per kilogram after you do the linear interpolation. This is when at VR is 84.5125. So 475.11. So let me write this one here. 475.11 kilojoule per kilogram. So we got U2. What else? Did we find everything? Oh, not yet. We didn't find U4. So do we know the temperature at number 4? We do not. Oh, that's a problem. Then let's see. What is the relation between 3 and 4? Between 3 and 4, that's an isentropic process. So can we follow the same process? Maybe yes. So it's an isentropic process. R is going to be V4 minus V3. V4 minus over V3 is going to be VR4 over VR3. Can we do that? Yes. What is the compression ratio? 8. Can we find VR3? Yeah. From where? From this temperature. From 2200 Kelvin, we can find VR3 because we know T3. So if you know the temperature, you can find any other property using this table. So let's go to 2200 Kelvin. 2200. So what is VR? 2.012. 2.012. So can you solve this one to determine VR4? Yes, you can determine VR4. This one goes here. VR4 is going to be this one multiplied by this, 16.096. Now, can you determine U4 from this VR4? Yes. Let's find 16 from this table. 16 goes up, there's no 16. 16 point what? 096. 16.096 is greater than this number and less than this number between these two. So can you find U? Yes, between these two numbers. So what do you want to do? Another linear interpolation. So U4 is going to be 897.3 kilojoule per kilogram at VR4 is 16.096. That's how you determine U4. Once you got U1, 2, U2, U3, U4, you're ready to solve the problem. 897.3 kilojoule per kilogram. So we got U1, U2, U3, U4. That's all. Let's determine the heat addition. Let's determine the heat addition. How do we determine heat addition? Heat addition takes place between 2 and 3. So do we know the equation? Yes, right here. Q23 is the heat addition, mass times U3 minus U2. So let's use this equation, mass times U3 minus U2. A Q23 is mass times U3 minus U2. We know mass here. We know U3 here. We know U2 here. So can you determine Q23? Yes. What is that? 0.6715 kilojoule. That was simple. B, the net work, W net. Oh, that one is slightly complicated. Why? How do you determine net work? Net work can be determined by W34 minus W12. That is mass times this one. Mass times U3 minus U4 minus mass times U2 minus U1. Then do we know all of them? Yes, mass here, U3, U4, mass, U2, U1. So can you determine W net? Yes, 0.3397 kilojoule. Thermal efficiency. Can you determine the thermal efficiency? Yes, W net over Q23. So this one divided by this one. So 0.506. That means 50.6%. And finally, the mean effective pressure. How do we determine that? Mean effective pressure can be determined by W net over V1 minus V2. Do we know W net? Yeah, from here, 0.3397. Do we know V in? Yes, 400 centimeter cube. V2, the compression ratio is 8. So V2 is going to be 400 divided by 8. 50 centimeter cube. Of course, you need to do a unit conversion from centimeter cube to meter cube. Then you get mean effective pressure. That's going to be 9.71 bar. So that's how you solve this problem. Any question about this? This difficulty is what you can expect from the final exam. Because not much I can change. So everything is the same. I'm going to give you table A22. You're going to determine M, U1, U2, U3, U4. Based on them, solve these. So determining the answer to each question is very simple. So it all depends on whether you can find the exact U1, U2, U3, U4. So if you miss one, you completely mess up the rest of them. So maybe I won't give too much credit for this one, but a lot on these. So if you miss, if it is, if it has like a 10 points, maybe 2.5, 2.5, 2.5, 2.5. Because if I give it too much credit here, if you miss one, you lose all the points. Doesn't make sense, right? Any question about Otto cycle? So that completes Otto cycle. Then the next one is diesel cycle. Is it difficult? Not at all. Diesel cycle and Otto cycle analysis, they look very similar. Look at that. Pressure 1 to 2. Isentropic compression. Pressure 1 to 2. Isentropic compression. Process 3 to 4. Isentropic expansion. Process 3 to 4. Isentropic expansion. Process 4 to 1. Constant volume heat rejection. Process 4 to 1. Constant volume heat rejection. The only difference, as you can see, process 2 to 3. So in the air standard Otto cycle, process 2 to 3 is constant volume heat addition. On the other hand, in air standard diesel cycle, process 2 to 3 is constant pressure heat addition. So that's the only difference. The energy balance equation for all the other three are the same. The only difference is process 2 to 3. So we are going to focus on process 2 to 3 and make PV diagram, TS diagram, energy balance equation, and that's all. Then we are going to solve one problem together that will complete Otto cycle and diesel cycle. You will see either Otto cycle or diesel cycle, one of them, in the final exam. So my plan is more like, the one problem from chapter 9, one problem from chapter 6, chapter 8, maybe two problems from chapter 6, because chapter 6 is more important because that's a theory chapter about entropy. Of course, you expect more than one problem, then only one problem from each chapter 8 and 9. There are 3 cycles in chapter 9, Otto cycle, diesel cycle. We are going to study both of them today. The last one is going to be this Thursday, which is Brayton gas turbine. So you can, there's only one problem from this chapter. So let's study PVPS diagram for this diesel cycle. And as you know, there are a lot of similarities between Otto cycle and diesel cycle. It is convenient to start from this one. So this is Otto cycle, right? Otto cycle. I think there was a movie called Otto or something. The guy called Otto, right? The old guy. There were two. One is Norwegian version, and the other one is Tom Hanks. You didn't see that? No? Okay, so the only difference is that process 223 is constant pressure process. So let's make PV and PV diagram together. So PV diagram, and TF diagram. Initially, isentropic compression, that's the same. 1, 2, 2. And here, the same. Isentropic compression. 1, 2, 2. Then, the number 2 is different. Constant pressure. Heat addition. So, constant pressure. P remains constant. P remains constant. P2 is the same as P3. And it's a constant pressure heat addition. So heat is added, therefore volume goes up this way. Number 3. What about here? Heat is added, therefore temperature goes up. What about entropy? Waste form of energy is added to the system. So entropy goes up because you have more waste. Then we have isentropic expansion. So it's an expansion process, pressure goes down, but volume goes up. Number 4, isentropic. Entropy S remained constant and heat is removed, therefore, isentropic expansion. So entropy remains constant. Since it's an expansion process, temperature goes down. That's number 4. And finally, constant volume heat rejection. Pressure goes down, volume remains constant. V1 is the same as V2, V4. And on this TS diagram, heat is removed. So temperature goes down and entropy goes down because waste form of energy is removed from the system. So there is S1 is the same as S2, isentropic process. Isentropic process between 3 and 4. So these are PV and TS diagram. And what about energy balance equation? Energy balance equation is going to be the same for all of them except 2 and 3. So let me repeat. This one, and this one. W12 is mass times U2 minus U1. W34 is mass times U3 minus U4. Q41 is mass times U4 minus U1. What about process 223? It's going to be constant pressure process. So we are going to use constant pressure process, this one, when heat is added. So Qin is mass times H2 minus H1 between 2 and 3. Q2 and 3 is mass times H3 minus H2. So that's how you determine the energy balance equation. And what is the main parameter, key parameter when you study internal combustion engine? The compression ratio. The compression ratio is between these two, V2, let's say V3. So the compression ratio is V1 over V2. That is compression ratio R. There's one more volume here, V3. So let's compare these two. That is called cutoff ratio. R of C is V3 over V2. That is only unique when you have a diesel cycle. Then, how can you determine the thermal efficiency? The thermal efficiency can be determined by desired output. over required input. So what is the desired output? So the desired output is so that power we develop. So we produce during the expansion process W3 to 4. So W3 4 is the power that we the work we produce. W12 is the work that we consume, and Q23 is what we provide. So the thermal efficiency can be determined by W3 to 4, this one, mass times U3 minus U4 minus W12, this one, mass times U2 minus U1 over Q23, this one, mass times H3 minus H2. So that's how you determine the thermal efficiency. So that's everything for the diesel cycle. Then, as we discussed in the previous Otto cycle analysis, the enclosed area is that determines the net work that you produces. So how can you increase the net work? You can compress more from here even further. Then you can add this much if you increase the compression ratio. Can we do that? Yes, when you have a diesel cycle. Why? When you have a diesel cycle, when you have an Otto cycle, we have an air-fuel mixture in the piston cylinder device. So when you increase the compression ratio, of course, its efficiency goes up. However, there's a possibility of auto ignition due to high pressure and high temperature, and that limits the compression ratio. So the MPG of gasoline engine is usually lower than MPG of diesel engine. On the other hand, when you have a diesel engine, we only have air in the engine. So we compress as much as we can. Then we inject fuel, so either the self-ignite, so we can achieve higher compression ratio. So higher MPG can be achieved when you have a diesel engine. So where do we use diesel engine? In an airplane? No. Usually like a dump truck or like container ship. So between dump truck and container ship, we focus on fuel efficiency because you may spend maybe $100,000 per day just to for the fuel. So in that case, we are trying to increase the compression ratio as high as possible. So if you find a diesel engine on those container ships, it's very tall. Why? The piston need to move a lot compared to a diesel engine in a commercial vehicle, gonna be short. So the efficiency of the taller diesel engine is usually higher. So that means that diesel engine is always the best because it has a high MPG? Not necessarily. The problem is that the high pressure can give you some negative effects such as environmental effect. And when you have a combustion in extremely high pressure, this nitrogen, which is supposed to be inert gas, is going to react with oxygen that produces what? Air pollution. So usually, it is not recommended for the passenger vehicles to use a diesel engine. But the years ago there was a diesel gate in the European automobile companies. You heard about that, right? So that actually gave a lot of the issues in terms of the air pollution because of this the limitation of diesel engine due to high compression ratio. So it has a pros and cons. The pros is the fuel economy. Bad means that environmentally bad. So that's everything for diesel engine and Otto engine. What happened? So let's solve one problem together about diesel engine, air standard diesel cycle, and that will be all for this. So if you go back here, you can see how many properties that we need to find. So one unique in this cycle is H2 and H3, because in the Otto cycle, we only focus on specific internal energy U, but this time we have H. So the properties that we need to find for air standard diesel cycle include H2, H3, and U1, U4. So when you have this air standard diesel cycle, what do we need to find is going to be U1, H2, H3, and U4. So you can see these two are different from the previous problem. And as I told you, whenever you see air standard cycle, you need to make two property diagrams. The first one is TV diagram, and the other one is TS diagram. TV diagram looks like this. Isentropic compression, constant pressure, heat addition, isentropic expansion, constant volume, heat rejection. 1, 2, 3, and 4. And we have V1 is the same as V4. P2 is the same as P3. What about on this TS diagram? Constant isentropic compression from 1 to 2, constant pressure heat addition from 2 to 3, isentropic expansion 3 to 4, constant volume heat rejection 4 to 1. So let's see, what do we know? We know the pressure at the beginning. So at number 1, we know P1 is 9.5, 95 kilopascal. And temperature T1 is 300 Kelvin. And at the end of heat addition process, so this is the heat addition process. At the end, number 3, pressure is 7.2 megapascal. That means P2 is also 7.2 megapascal. Temperature is 2150 at number 3. At number 3, temperature is 2150 Kelvin. So let's solve this problem. Of course, we are going to use the same table, table A22. What is the main property that we need to know is the temperature. So if you know temperature, you can find any properties. So how many temperatures do we have? 300 at number 1, 2150 at number 3. So T1 is 300 Kelvin. T3 is 2150 Kelvin. Can you find U1 and H3 directly from the table? Yes. So let's do that. And 300 at 300 Kelvin, U1 is 214.07. 214.07 kilojoule per kilogram. directly from table A22. What about H3? The temperature is 2150 Kelvin. 2150 here. So H is this one, 2440.3. 2440.3 kilojoule per kilogram. I'm pretty sure that you will find these two values very easily. Now the problem is this one and this one, right? What is the relation between 1 and 2 and 3 and 4? Isentropic compression, isentropic expansion. So when you have an isentropic process, what is the equation that we can use? Where is it? Where are you? I don't see it, but that's okay. So when you have an isentropic process, S1 is the same as S2, we can use this relation. V2 over V1 is VR2 over VR1. You remember from the previous example, right? And there's one more equation. P2 over P1 is PR2 over PR1. So do we know P2 P1 or V2 V1? Let's see. We know P1 here. We know P2 here. Okay, so we know P2 over P1. So let's use this relation. P2 is 7.2 megapascal, 7,200. P1 is 95. So if you can determine PR1, we can find PR2. So let's find PR1 from where? 300. So at 300 Kelvin, we can find PR1. At 300 Kelvin, PR1 is this number, 1.386. 1.386 at 300 Kelvin. Done. We have everything but PR2. Can you find PR2? Yes. We found PR2. Let's go in here. PR2 is what? 105.04. Then, can you find H2 at this PR2? Yes. PR2 is 105. So let's see. PR 105. Oh, they are too small. PR 105. Oh, that's not here. Go to the next slide. PR 105. Oh, 105.04 is between these two numbers. So H value should be between these two numbers. Then how can you find H2? Linear interpolation. So if you do linear interpolation, you get H2, that is 1022.82 kilojoule per kilogram. That wasn't difficult. Now, the ugly part comes here. This one is very ugly. So don't be mad. Now, let's use this one between 4 and 1, 3 and 4. So 3 and 4 is the problem. We can use this relation one more time. So it is V4 over V3 is VR4 over VR3. Can we find VR3? Yes, from this temperature. At 2150, VR4 is going to be 2.175. 2.175. So if you know V4 over V3, you can find VR4 find U4, right? So let's find V4 over V3. Unfortunately, this one is not easy. So V4 is the same as V1, right? So I'm going to say this one is the same as V1 over V3. No problem, because V1, V4, they're the same. It's a constant volume process. Now, can you find V1 over V3? We don't. So we are going to change this one a little bit. V1 over V2 times V2 over V3. Then, do we know V1 over V2? Can you find V1 over V2? Yes, by using this relation. This V1 over V2 is going to be V1 over VR2. Can you find VR1 from this temperature? Yes. Can you find VR2 from this PR2? Yes, you can. But it's going to take a lot of time, right? So VR1 first. Temperature is 300 Kelvin. So let's go to 300 Kelvin. Here, VR1 is going to be 621.2. This one is 621.2. VR2 can be found from this PR2. So where is PR2? Between these two numbers. Can you find VR2? Yes, between these two numbers. How? Another linear interpolation, unfortunately, right? So VR2 is what? 26.793. So finding V1 over V2 is not a problem. What is a problem? Because you need to do two linear interpolation, right? But now the question is V2 over V3. Can you find V2 over V3? What is the relation between 2 and 3? Constant pressure process. When you have a constant pressure process, and this is an ideal gas, in chapter 3, we studied this one. T2 V2 over T2 is going to be P3 V3 over T3. Do you remember that in chapter 3? Yes. When we study ideal gas for the first time, right? Right? Yes. So it's a constant pressure process. P2 P3 goes away. So if you move this one to the right left-hand side, move this one to the right-hand side, what we get is V2 over V3 is the same as PT2 over T3. So this one is T2 over T3. Do we know T2? Do we know T3? Yes, 2150 Kelvin. Do we know T2? You can find it from another linear interpolation between 960 and 980. So there are three linear interpolations. That's not my fault. So the temperature is going to be 979.6. So we have everything. Can you determine VR4? Yes. What is VR4? VR4 is going to be, I know this one looks very complicated, but VR4 is going to be 22.98. Let's find U4. VR4 is 22.98. 22.98. It's between these two numbers. So if you want to determine U4, unfortunately, we need to do another linear interpolation between these two numbers. It's just taking time, not that difficult. So if you do, U4 is going to be, where is it? 785.75 kilojoule per kilogram. That's how you determine this 4. The rest of them is simple. We don't have time. We will do it on Thursday, but you can see When you have a diesel cycle, the problem is going to be here. Finding the last one is going to be the problem. Takes time. So, which one is going to be in the final exam? Otto cycle or diesel cycle? I don't know yet. So it depends on the difficulty of the other three problems. If I see the other three problems take too much time, I will give you Otto cycle. If not, diesel cycle. But not both.